The area function is interesting in that the variable that goes into it is a little different than what we're used to seeing. Here's how it works. When you have some function, we'll call it f of t, where t in this case is on the x-axis, and you want to compute the area between some starting point a and some second point x. Okay, so here's our x. Our variable is going to be the second point, and this thing is going to move back and forth along the t-axis here. So t is our variable down here on the axis, but x moves back and forth to tell our area function where to stop. And then the area, because I'm getting ahead of myself, the area function tells us the area between a and x. So it gives us that area under the curve between a and x, and then we can slide x around, whereas t stays fixed. And note that we usually use capital letters for these area functions, so you might also see this written as like capital F of x or capital G of x, something like this. But let's get a formula for the area function, and you probably guessed that it's going to use an integral. Okay, here we have it. The area function equals the integral from a to x of f of t dt. This works because the integral gives the area under the curve, and then we let x be the upper limit of integration here, vary. So as we let x get bigger, this is going to include more and more and more area. And of course, as x gets smaller, it's less. So this works, but it's a very unique function because we're used to seeing x inside the function down here, inside this little f of t, but now it's serving as the limit of integration and the edge of our area that we're interested in. Now, there's one important property of this area function that really makes it work for us mathematically, and that's that a of x gives what's called the net area. And that just means that the area above the x-axis is positive and the area below the x-axis is negative. So don't get that confused with what we'll call the total area, which is just the geometric total area trapped between the curve and the x-axis, regardless of if the curve is above or below the x-axis. So let's do an example using this net area and the area function. This example will be referring to this graph over here. This graph is of f of t, and then we'll be taking the area of various chunks of this graph. So it says consider two functions. F of x equals the integral from 0 to x of f of t dt, and g of x equals the integral from 2 to x of f of t dt, where f of t is the function shown in the graph. So note that capital F of x and capital G of x are both area functions. The only difference between them is where they start. One starts at 0 and one starts at 2, and then we're asked to compute all these values. So I'll just do them, but as soon as you get the hang of this, please pause the video and do the rest yourself, because really these kinds of questions are actually pretty fun and fairly approachable. Let's take a look. For part A, we have capital F of 2. So that's saying find the area between 0 and 2. So 0 to 2, f of t dt. Okay, you wouldn't even necessarily have to write that, but just to be very clear. So what is this? Well, here's 2 right here. So it's just saying what's the area between 0 and 2 on this graph. And note that area above the x-axis will be positive and below the x-axis will be negative. Well, all there is for f of 2 is this area of 8, right? That's all that is in this green area. That's all we're asked to compute. So this simply comes to 8. Okay, let's look at capital G of 5. Okay, well, this is the integral from 2 to 5 of f of t dt, f of t dt, and we can see from the graph, what is that? Well, we have 2 to 5. It's just this area in here. Now, this area is 5, but because the area function gives net area, and that area is below the x-axis, it's going to give us negative 5 for a final result. Okay, part C says capital F of 0. Okay, so we could write this out if we're feeling up to it, though it's not really necessary. We could easily just write 0, but this is technically the integral from 0 to 0 of f of t dt. That's actually one of our properties of integrals too, that the integral from 0 to 0 always equals 0. But we wouldn't really need that property because we can see very clearly from the graph that that's the case. On to D, we have capital G of 8. Okay, well that's the integral from 2 to 8 of f of t dt. And we can look at our graph up there and see what that says. We're starting at 2. We're stopping at 8. So we have both these areas of 5 and 11. Both of these are below the x-axis. So it's going to be -5 plus -11, giving us -16. These are so nice. I could do these all day. Capital F of 8. Okay, well that's the integral from 0 to 8 of f of t dt. All right, so over on our graph, we're going all the way here, here, and here. We're starting at 0, so we're going to be doing 8 for the positive area, minus 16 for the area below. 8 minus 16 gives us, of course, -8. Moving on to part F, we have capital F of 5. Well, that, of course, is simply the integral from 0 to 5 of f of t dt. And we can see very quickly that that's the area of 8 minus the area of 5 for a net area of +3. Finally, for part G, we have capital G of 2. Well, this is another one. Whoops, integral from 2 to 2 of f of t dt. I don't even need to look at the graph. I know that that's going to be 0. Even if we did look at the graph, there's not much to say, right? It would start and stop right at 2 here. So if there's no space, there's no way to trap any area. So of course that area would be 0.